This is a question based on aromatic chemistry. It also includes a 6 marker. Two sections, A and B. Try both of those, and then when you're done, review your answers. Here's part A, the 6 marker component. And here's part B. Okay, so starting the review, it is asking you to use the data within your answer. So that's a key giveaway that you're going to have to do some calculation with what we have here. But much of it is actually about understanding the bonding within a benzene molecule. Going to put up how the level is determined, whether you're a level 3, 2 or 1. As always, if you cover all 3 of the stages well, you'll get into level 3. If you cover 2 of them well, or you attempt all 3 of them, you get a level 2. And if you complete 1 of them well, or attempt 2 of them, you get in to level 1. So let's look at the first stage that you need to cover, and that's the bonding within benzene. So keeping it really simple to begin, each carbon is bonded to 3 other things. It has 3 covalent bonds. Spare electrons overlap, and that's what gives rise to the delocalized ring in the benzene molecule. So that is one stage completed, and you have now got level 1. You're moving into 1 or 2 marks. The shape, well, because there are 3 covalent bonds, that makes us think trigonal planar. It's a planar structure. The bond angle is 120 degrees, and what we have is a planar hexagonal ring. The CC bonds are equal in length. Now that's a really important distinction because we know that there is a difference in size between single and double carbon-carbon bonds, and that's actually part of the evidence that was used to dispute Kekulé's theory. Moving on to stability for the third stage, well, we can look at the fact that we would expect cyclohexane-1,3,5-triene to be negative 360 kilojoules per mole. That's because that's 3 times the amount of cyclohexene. But the reality is that it's less. It's only negative 208, so it's much less exothermic than expected. What does that tell us? It tells us that the benzene is more stable, covering not a huge amount of content, but those facts gets you up to the level 3 and 5 or 6 marks. Moving on to the final part of the question. Why is cyclohexane-1,3-diene not exactly double the enthalpy of hydrogenation value of cyclohexene? I'm going to start off by drawing out the 2 examples. And I'm going to show that those 2 double bonds are quite close to each other. They're only separated by 1 single bond. I'm going to talk again about that in a minute. Now, in terms of the value, it can be anywhere in the range negative 239 to negative 121. It has to be more exothermic than cyclohexene, but it can't be as much as twice. But you've got this huge range of acceptability within. Why? Well, the double bond is separated by 1 single bond, as my diagram shows. Well, when we think about what happens in benzene, where the electrons start to overlap and we get the pi bonds, the same can happen here. We can get some delocalization. That makes it slightly more stable, and therefore it's not going to be double the level of energy released.